A wide range of studies in the physics department falls under the category of atomic, molecular, and optical physics. In his laboratory, Professor John Thomas studies the behavior of small clusters of atoms.
Just as this ball is confined in a trap by gravity, the atoms in our lab here are confined in a bowl made out of laser light. So optical traps work by just using a focused laser beam in a high vacuum to polarize atoms. And what they do is they attract the atoms to the region of the highest intensity where the focus is. When you focus a laser beam down, you create a confining region that looks very much like a bowl that's made out of light. And so the atoms vibrate in that bowl the same way as a marble vibrating in a glass bowl. And we found that the best traps that people were using would only work for a few seconds. If the laser intensity fluctuates, it's kind of like taking the bowl and having the sides of the bowl do this. And so the atoms are oscillating back and forth in the bowl, like marbles in a bowl, but we're hitting them in the face as the bowl fluctuates in depth. And if they're hit at twice per cycle, each time they reach one side of the bowl, they're hit, and they hit the other side and they're hit. If the bowl fluctuates at twice the frequency that the atoms vibrate, it will heat them up. So we realized that we needed to develop a very stable laser, and we switched to using what we call an ultra-stable CO2 laser, and we found that we could hold them for up to 400 seconds. And so the system worked exactly as it should, and the 400-second lifetime is actually just determined by how good a vacuum we have. So our vacuum was down below 10 to the minus 11 torr, and at that vacuum, a few hundred seconds was the right number. But the real goal, once you have a working optical trap, is to get the atoms then as cold as you can get them. And the workhorse for that is evaporation. And so once you have the atoms in this perfect frictionless bowl made out of light, they evaporate the way alcohol evaporates from your skin. And so basically the atoms collide and share energy. One of them gets enough energy to jump out of the trap, and the remaining atom is much, much colder. And so with that process, we could cool the atoms down to maybe 100 billionths of a degree above absolute zero, and we could create the first degenerate Fermi gas that was created by optical means. And it turns out if you apply just the right magnetic field, you can make spin up and spin down atoms very strongly scatter off of each other and very, very strongly attractive, and create what is really the most strongly interacting non-relativistic system known, because it turns out you have to apply quite a big magnetic field, about 830 Gauss in our experiments. And if you applied such a field to an old-fashioned magnetic trap, you would flatten the trap out and all the atoms would leave. Whereas with our optical trap, we were in the perfect position to do these very beautiful experiments involving strongly interacting matter. And that was actually a primary motivation for creating the optical trap in the first place. We managed to connect to all these different fields, from high temperature superconductors to neutron matter to this quark-gluon plasma to string theory. And so the strongly interacting Fermi gas is a very rich system. One of the most beautiful ways to show that the gas is strongly interacting is simply to collide two clouds of atoms together. And at that point, the gas has the shape of a cigar, but we could cut the cigar in half by using a repulsive green beam laser, and we cut the gas in half into two pieces. You can let the clouds of atoms move toward each other and hit so hard that it's as if liquid metal was hitting, and they create shock waves. And we end up observing very, very beautiful shock waves. And so we have a movie of that. We can actually watch the clouds hit and expand outward, creating these shock waves. When we turned off the optical trap and let the gas expand, we found that it would expand in this perfect elliptical way, standing still in the long direction of the cigar and expanding only in the narrow direction as predicted by two Italian theorists. And so we took a movie of this expansion, one shot at a time. We could watch the cloud expand from a narrow cigar into an ellipse. So at NC State, there are several theoretical groups which overlap very strongly with our work, and the overlap ranges from quark-gluon plasma to nuclear physics to condensed matter. And so we have theorists in all these areas that overlap just beautifully with the type of work we do. which is one of the things that makes this department really attractive. There's a very, very good connection between the theoretical groups and the experimental groups.
From strings to quarks to atoms to molecules, NC State's atomic, molecular, and optical physicists ply their trade in a wide range of arenas.